Good. Always nice to see some calculus stuff. I don't have that many calculus students this year. So it gives me a good chance to review this stuff, which I haven't had to do for a while. So are we on the same document?
No, let me send you my new one.
Okay.
Sorry, I thought I signed up for the 11 Mountain Time, not the 11 my time. So.
Yeah, it came through on my calendar as 10. I don't know.
Yeah, you're good. I'm just.
Yeah, no, that's fine. Let me close this one out. Did you do okay on that test?
I got a 75, which isn't horrible, but which is really good either.
Yeah.
But her tests are really hard because she grades so nitpicky on all the work.
I like her problems. They really are a good test of the calculus in that particular type calculus. Have you done integration by parts yet?
Not really, I don't think.
Okay. No, I think the way they do it anymore is they do integration by substitution, and then they go back and work on all of the stuff like area between two curves, volume of objects, and all of that good stuff. And then once you get through all of that, then you'll go on and learn, well, maybe not even this year. You might be done with new material pretty quick here. When's your school then?
My final's next Thursday.
Okay.
What's it for this class? So I'm done next week.
Oh, earlier than normal.
Yeah, it's earlier than most high schools.
Okay.
So I have a couple problems.
Where to begin?
Let me look. I've done most of this.
Okay.
And so, let's see. Can we start on 15?
So the hypotenuse of a right triangle is always 10. One leg decreasing at a rate of find the rate of change of the other at the instant m equals 6. Okay, this is the classic related rate problem. So almost all related rate problems, you kind of want to draw a picture. Okay. There's our triangle, the hypotenuse. There's our right triangle. The hypotenuse is 10 feet long. One leg, we'll call it this one, L, is increasing at a rate of 2 feet per second. What does that mean?
Is it just...
It means dl dt.
Okay.
So dl dt, because it's with regards to time. And most of these related rate problems are always with regards to time. Okay? And that's 2. Okay, and then the other leg, they want us to find the rate of change. So they're looking for dm dt. So that's what we're solving for. Tell me the master equation that governs this picture. That's always the next question you want. In fact, that sometimes is the first question, as opposed to writing out these things over here. But this is important also, writing out what they give you and writing out what they're looking for in terms of differentials. Okay? So, what equation governs my triangle?
Is it just a squared plus b squared equals c squared?
In this case, what is it?
It's m squared plus dl dt squared.
Oh, plus L squared.
Okay.
Equals 100.
Okay.
In other words, this is our master function. And all of these related rate problems are always you're gonna start with this master equation. And one way you could look at this problem is this is a ladder leaning against a wall, gradually slipping.
Okay.
Actually, not gradually slipping. Yeah, let's make this a little more understandable and make M be 2, and this is what we're trying to find. I guess we can't do that. We'll just have to live with what they've given us. I can't use the ladder because it's not slipping. Okay, what we know, here, let me write what we know over here. dl dt equals 2, and we're looking for dm dt. In other words, since dl dt is a positive number, what's happening? It's expanding. It's getting bigger. So it's the opposite of that ladder slipping. I would prefer a ladder slipping because that's more real world. But it doesn't matter in terms of the calculus. In terms of the calculus, it doesn't have to be a ladder. It's just a triangle that is changing. Now, almost always the next thing you do is you implicitly differentiate this master equation here. So, implicitly differentiate it with respect to time. What do you get?
So is it just dm dt m squared?
First, you explicitly differentiate that, and then you follow it with a dm dt. And you do that with everything. First, I explicitly differentiate it, and I follow it with a dl dt. And now I differentiate the right side, and that's 0. Okay? Now I can substitute. Here's what I'm solving for, which means I have to substitute something for m, I have to substitute something for L, and I have to substitute something for dl dt. Well, they tell us that m is 6, so I've got 2 times 6. This is what I'm trying to solve for, so I'll leave that like that. Plus, what is L when m is 6? Solve that. Substitute 6 for m and solve for L.
Eight.
Okay, so that's what L is. Notice they didn't give us L, but we can always solve for L because we know two sides of that right triangle. And we know dl dt is positive 2. Now we can solve that. we get dm dt is going to be 32 divided by 12 negative 32 divided by 12. And that is going to be in the same units as everything else, feet per second. I think I did my math right. Yeah, 32 divided by 12.
Yeah, looks right.
Remember what they're asking for. This is an instantaneous rate of change. So this rate of change of 32 per 12, first of all, means that m is shrinking, not increasing. If the ladder was sliding down the wall, m would be increasing and L would be decreasing. But the fact that they told us L, I should have labeled it the other way around. Then it could have been a ladder sliding down the wall. But like I said, it doesn't matter. If L is increasing, then M has to be decreasing. And it's only at this specific point in time when M is exactly 6. Because 1 second later, M isn't going to be 6 anymore. 1 millisecond later, it's not going to be 6. So all of these related rate problems pretty much unfold the same way. You figure out a master equation, you implicitly differentiate it, and then you fill in everything but one thing.
Okay.
It allows you to solve them. Okay, what else? Or what next?
16b.
Okay. Okay, so find the absolute max and minimum. What's our goal gonna, or what's our task gonna be?
I don't really know.
What's always the first step? Almost always. Take the derivative.
Take the derivative.
If you don't know what to do, that's always a good place to start. Unless you're dealing with strictly integration, and even on most or a lot of integration problems, the first step is take the derivative. Notice that on any u substitution problems, the first step is, once you've defined u, is to figure out what du dy is, or du dx. So that's going to be our first step. Take the derivative of that. Well, let's write it so that we can take the derivative using the product rule. In other words, we're going to write it not with radical signs, but with fractional exponents. So that's what g of x is. What's g prime of x?
One, and then 1/2 x minus 3 to the negative 1/2.
Okay, hold on. Stop there. If y equals u times v, y prime, and I like to have students always do this the same way. In other words, I know you can do it in either order, but the easiest way to never make a mistake is to always start with the first function, u, and then take v prime, and then add the reverse. Means it's got to be u prime v.
Oh, yeah.
What you did was you took the derivative of both of them.
Yeah.
All right, so let's start over again. And even though you can do it in this order, you could do this one first. just for the purposes of tutoring, do this one first so I can follow you. I can't follow you when I don't know which one you're doing first until you're halfway through. And then I see what you've done wrong. But okay, so what's the first?
So it's x and then 1/2 and then x minus 3 to the negative 1/2.
Okay.
And then plus 1 and then x minus 3 to the 1/2.
Yeah, I don't typically write the 1.
Yeah, but I just do it just because.
Well, there's nothing wrong with it. I don't have any problems with that. Okay, now, where are our minimums and maximums, absolute or otherwise, going to come? Where is our absolute maximum going to occur on this? And there has to be one. That's one of your theorems. I can't remember which theorem that is. Maybe Raleigh's theorem, but on a continuous function, on a closed interval, there has to be a maximum. So, here's the rule. It is going to occur where this derivative is either equal to 0 or not defined or at one of the end points. For example, if I had a function that was like this, and in other words, if I graph that function and it came out looking something like that, and I want to know where the maximum is between 3 and 12, I have to check this point because I have a 0 slope. I have to check this point, not because I have a 0 slope, but because it's not defined there. You can't differentiate that point. It's a cusp or a corner is what they call it. And I have to check this point here, and I have to check this point there. In other words, I got to check those interior points, and I got to check the endpoints, whichever one gives me the highest number, that's my maximum. Whichever one gives me the lowest number, that's my minimum. But it has to be in one of those 4 spots. I do not have to check this part of the curve. Cannot be there. There's only 4 places it could be, and that's where that first derivative is 0, not defined, or the end points. So let's simplify this a little bit. It's going to be x in the numerator, x minus 3 to the 1/2 times 2, that's this part, plus x minus 3 to the 1/2 in the numerator. So let's do the easy part first. Where is it not defined? Where is it not differentiable?
At 3.
Correct. So x equals 3 is one of our possible points. It's not differentiable there. Now, is there any place where it's equal to 0? Well, if I do this, let me think if I can even do it the easy way. Yeah, I think I can, at least for purposes here. If I multiply both sides of the equation by x minus 3, to the 1/2. In fact, let's do it by 2 times this. Here's what I get. I get x plus 2 times that to the 1/2 times that to the 1/2, which makes it just that. You follow that?
Yeah.
In other words, I've simplified that considerably. I've basically gotten rid of all denominators, and now I'm going to get rid of all parentheses. So 0 equals 3x minus 6. So x equals 2 is this point. Wow, I'm going to be impressed if this curve I drew is anywhere close to being correct, because I didn't intend it to. I was not trying to approximate this function, but so far it's right on. And we're evaluating it on the interval 3 to 12, the closed interval 3 to 12. So they're only looking at this part of the curve, if I call that 12. They don't care about this 0 that comes at x equal 2. That's not even in the interval. And notice why x can't be equal to 2. Gives you a negative number in your radical. So x equal to 2 isn't even a solution to this. There actually is no spot where, because x equals 2 is outside of my domain, not even to mention the interval. If I graph this, it won't even be on there because they'll graph it only across the domain. So now I really only have 2 points, and that is I've got to evaluate it at 3 and I got to evaluate it at 12. Well, what's g of 3?
Zero.
What's g of 12?
36.
There's your absolute maximum, there's your absolute minimum. 0 and 36. 16b. Let's just always like to double check.
I don't have the answers on that one just because it separated them. So I'll look.
That's okay. That's fine.
Yeah, 0 and 36.
Okay. What next?
20.
Okay.
I spent like 8 hours doing this last night, so
Ain't calculus fun?
yeah, it was nice and joyful.
Oh, that's okay. When you get done, you're going to be feeling very accomplished because you're going to have learned something that not very many people learn. 20, you said, right?
Yep.
Okay. All right. Find the dimensions of the box with the largest possible volume. Don't tell me that. Just a second. Huh. Fixed itself. So, that's where we're going to begin. We're looking for the box with the largest possible volume. What's the master equation for a box?
Length times width times height.
Volume equals length times width times height. Okay. So, a rectangular storage container with an open top is created when the length of the base is twice, where the length of the base is twice its width. Well, that means I can change this to make it 2W times W times H, right?
Mm-hmm.
Okay. Material for the base costs $5 per square meter. Material for the sides costs $3 per square meter. If you have $15 for materials, what is the biggest box you can build? So, this is probably one of them you spent a long time on.
Yeah, because I didn't understand why you couldn't just make it really narrow just to cut out more price for the base, because it doesn't tell you how high like the base or the height can be.
Right. Now, let me think about this for a second. They've added a twist. So let's talk about surface area. In other words, there is another equation that's at play here. And that's almost always the case whenever you have optimization problems, which is what this is you have another equation somewhere. Okay? In other words, right now I've got volume as a function of both W and H, and I don't really want that. I want it to be a function of one variable only, and then I can maximize it. In other words, I can take the derivative of it, set it equal to 0, and figure out what that width would be. So our other equation is in regards to the surface area. Materials for the base. So the surface area equation, here, let me go down here. Surface area equals the it's the area of the base, which is width times length, which is 2W, plus there's 4 sides. Every side of the box has a surface area of length times height, right?
Or would you have to do it 2 length times height times 2 width times height, or plus 2 width times height?
You might be right there. I didn't quite figure out this. Yes, you're absolutely right. In other words, we have the surface area of that and that. Here, let's do this again. That's the surface area of the base. Plus 2 length times height plus 2 width times height. And L can always be turned into W. So here's what we got for surface area. 2W squared plus 4WH plus 2WH. That's our total surface area.
Okay.
What's the total cost of our materials going to be?
15.
Well, it's going to be $5 times the base. Well, there's the area of the base. So it's going to be 5 times 2W squared plus all of this other, which looks like 6WH, is going to cost $3. All right, let me write that up here so it's not confusing. So there's the cost of our material. And notice that it's totally a function of W and H. right here.
Yeah.
And we know what the cost is, 15. So I can substitute that. Now, see what I'm leading up to here. I'm trying to get a volume function that is a function of one variable only. I can now do it. In other words, this second function that we came up with based on their restrictions allows me to solve for h in terms of w. I can then solve and substitute something for h that's a function of w, and now bingo, really easy at that point. So, assuming I haven't made a mistake here in my math, and once again, that's not always a valid assumption. Oh, incidentally, did you get my answer on that other one? It took me about 2 minutes to figure it out after we hung up.
Yeah, I did.
And you understood
And then,
it?
yeah, I was able to,
Yeah,
once I found like it,
was u equal to t cubed and not what I originally had tried, which was u equal t cubed plus 1, which didn't even make any sense. You couldn't do it the other way. All right, so first of all, let's see, what should I do here? I've got 15 equals 10w squared plus 18wh. Well, if I want to solve that for h, I got to get everything else on the other side. 15 minus 10w squared equals 18wh. So h equals all of that divided by that. Now I've solved for h. I can go back into this function. And so volume equals 2w squared times h. And that's h right there. So there's my function. Notice that it actually simplifies fairly easily. What does it simplify to? It simplifies to, here, let me start writing up here in the upper top. I think I don't need a lot of white space for this. So I get v equals, I'm going to cross off that, and I'm going to make that a 9. So I've got, distributing my numerator, 15w minus 10w cubed all over 9. Correct?
yep.
Okay. Now is all we want to do is differentiate that. I can separate it into two fractions. So v prime equals 15 ninths minus 10 thirds w squared.
Yeah.
And this is, let's see, 3 goes 5 thirds. So that's 5 thirds. And now, if I'm going to set all that equal to 0, then I've got minus 5 thirds equals minus 10 thirds w squared. 3's cancel, those cancel, you get w squared equals 1/2 w has to equal root 2 over 2. Check and see if that's correct.
It says
So
root of 0.5.
Oh, really?
Yeah.
I got a w squared of 0.5. I wonder if somehow I got w cubed here when I was supposed to get w squared. Because then I would get 0.5, a w of 0.5. That's what they're saying, which means a length of 1 and a height of whatever it turns out to be. Well, matters not. I'm 100% sure we did the problem properly. So once again, I think I've just made a math error. There's quite a bit of complicated algebra in that problem, particularly since the second function is a complicated function. This function right here is algebraically somewhat difficult to solve. And then you have to substitute whatever h is back into the original function. So you end up with a fairly complicated one. And I suspect that that should have been w squared. And then if that's w squared, then I get this exact thing, and I get w equals 1/2. Rather than trying to find our mistake, let's go to another problem.
Uh, 23.
Okay. These are always classic questions. If you're taking an AP Calc exam, you're going to see a problem on an object moving along a path. Usually it's an object moving along the x-axis, but this doesn't have to be the x-axis. In fact, it doesn't have to be a straight line, it looks like. But I would think it does have to be a straight line, actually. This path right there has to be a straight line. Okay, so we got the acceleration. First of all, know this. S of t is position. S prime of t is what? That's the same as velocity.
Yeah. And then
Is v of t. And then S double prime of t
is acceleration.
Acceleration, which is a of t. So they've given us an acceleration function here. And what we got to do is kind of work our way backwards. We got to work back to that, and then we got to work back to that to figure out what the position is. Okay, so how do I get from second derivative to first derivative?
Antiderivative.
Correct. So give me the antiderivative. In other words, tell me what v of t is.
It is 12t.
The antiderivative. Remember, we're going the other direction.
So it's...
Start with the exponent, add 1, divide by the new exponent.
Oh, okay. So it's t cubed, so 8t cubed
Keep going.
plus 3t squared
Keep going.
plus 4t plus c.
There you go. That's the most important part, is the C. Because, ooh, they're going to really make this tough. In other words, normally they give you the initial condition for the velocity. They would tell us what v of something was, and then we'd solve for c, and then we'd repeat the step. But they don't tell us anything about an initial position of v. So let's go straight to s. I'm going to do this quickly just because I want to make sure we get done with this problem. And I'm not 100% sure I know how to do it. I think I do.
So wouldn't you just plug in
There you go. There's
0? Wouldn't you just plug in 0 for...
Now I can. Notice I couldn't before. I had to get to the position function before I can use any of these s of zeros and s of 1. So
Yeah.
I took my velocity function with c being unknown, and I found the antiderivative of it, which I believe I've got here correctly. Now they're going to give me two simultaneous equations. One of them is s of 0 equals 3. So what does that tell me? That means that in my particular case here, that's equal to 0 plus 0 plus 0 plus 0 plus c. So that tells me what this c is. That c is 3. Now this c should also be 3. I don't think it's a different c. So that's equal to 10. Let's see. I plug in 1, I get 2 plus 1 plus 2 plus t is 1 and c is 3. No. That becomes c. That c is 1. That is a different c. Yes, and it can be a different c. This c here does not have to be the same as that c there. And I'll prove it. What's that?
That second c is 2, not 1, because 5 plus 3 is 8.
Correct. Yes, you're right. It is 2, not 1. Okay, so here's our final position function. S as a function of time is 2t to the fourth plus t to the third plus 2t squared plus 2t plus 3. And we can furthermore prove that s of 0 is 3 and s of 1 is 10. Furthermore, we can differentiate that twice and come up with the acceleration function that is precisely that. So after doing all those checks, you know, if you were working for the Mars mission and you wanted to know exactly what the position of the object is after t seconds, that's what it is. After t seconds. Go ahead and look it up, make sure we got the right math.
Yep, we're good.
Yeah, the only thing I was a little confused with, and I see why now, is the fact that I should have used a C there, but then I should have used a D. I should have used another variable. In other words, that last number is merely some number. It doesn't have to be the same as the previous some number. And once you do that, now you can immediately solve for D, and then you can solve for T without any confusion. Okay? What next?
Look, to be honest, I thought that was as far as we were going to get, so.
Well, we skipped around pretty good. We haven't, you want to go backwards?
Yeah, can we go to 11 and just explain what she's asking?
Uh-huh. Ooh.
Because I don't really know how to verify that. I just kind of know that is supposed to be like that.
Well, that's an identity. We know that the derivative of tangent is secant squared. Let me show you how you can prove it to her. The ultimate proof, of course, is to show that tangent of x plus h minus tangent of x divided by h, the limit of that goes to secant squared. And that's going to be a tough proof. I'm not sure I know how to do that proof. But what I do know how to do is tangent is equal to sine over cosine. Okay?
Yep.
So let's take the derivative of sine over cosine using the quotient rule. Apply the quotient rule.
So is it just...
What's the rule? You got to memorize the rule. Unless she gives that information to you on these tests. You got to know all four rules. You got to know your product rule, your quotient rule, and your chain rule, as well as your power rule. Okay, quotient rule, really easy to memorize. The only thing you have to memorize is you start with the bottom, you end with the bottom square.
Is it low D high, high D low over low squared?
If that's the way you've memorized it, that's fine. I don't know. I do not memorize it that way. My way is shorter. Start with the bottom, end with the bottom squared. You're never forgetting that one. Here's what I mean. I'm going to start with the bottom. Well, we know it's multiplied by something. What must it be multiplied by? The derivative of the top.
Which is...
Right. And then order matters. That's why I had to start with the bottom. I couldn't do it in either order like you can do the product rule. You've got to do it in a certain order because you're doing subtraction. So I know that's a subtraction sign. And I know this has got to be just the reverse. So I'm going to take the derivative of the bottom, which is negative sine, and multiply it by the top. And it's all going to be over the bottom squared. Now, our goal is to prove that that's equal to secant squared. Well, what do I got? I got cosine squared of x plus sine squared of x all over cosine squared of x. What's cosine squared x plus sine squared x?
1.
What's the reciprocal of cosecant or cosine?
Secant.
That's how you do it. Now, that's one way to do it. Just in the interest, she may want you to be doing it this way. She wants you to take the limit of f of x plus h, which is the tan of x plus h, subtract off f of x, which is the tan of x, divide the whole thing by h, find out that limit as h goes to 0. Now, to solve that, you would have to use the sum and difference identity for tangent. You may end up having to turn this tangent into sine over cosine to solve it. I don't know. I've never tried to prove this identity using the limit quotient definition. It's far easier to prove just by taking the derivative of sine over cosine using the quotient rule, but I'm not sure if that's what she's looking for here. I'm not sure that counts. That actually, the fact that she used the word verify, yes, definitely the way I did it. If she'd have used the word prove, then I would say you'd have to do it this way.
Okay.
But the mere use of the word verify, that's what you do in trig half the time, is you verify trig identities. And so I'm almost now 100% sure that she wanted you to just substitute sine over cosine, take the derivative using the quotient rule, and you end up getting secant squared. Okay, what else? We got going 5 minutes late. We can go for a little bit more.
To be honest, I think I'm pretty good on everything else.
Okay.
I'll probably get another tutor session like Tuesday because my test is Wednesday, and I'll spend another like 6-7 hours doing this, and I'll be able to tell you exactly what I haven't gotten down to the T yet.
Does she have an answer on 11?
Her answer, let's see.
I bet she did it just substituting sine over cosine for tangent. And then you could actually do it either way. I could do it the other way. As long as I substituted sine over cosine, then I can do it the other way.
Her answer for 11 literally just says express tan x as sine over cosine x, and then apply the quotient rule.
Just exactly what I did the first time.
Yeah.
Okay. You good to go for today, Mitch?
Yep. I'm going to spend another like 6 hours in the library after I go eat. So
all right.
I
will probably
figure out
Tuesday morning.
Yep.
All right. Bye-bye.
All right, bye.